Okay, so let's get started. So this problem should we discuss or everybody is comfortable doing it? We can go to the next problem. Do we need to discuss or can we go to the next problem? Somebody say something. Otherwise, I'll do whatever is required.
Yes, sir, we can discuss.
We can discuss. Okay. Okay. So let us very quickly discuss. So we want things to be calculated per metric ton of pure ethylene glycol. Now you can start it any way you want. Just one way we can think about doing this. One way we can think about doing this is to start from the product end. That is what we want. That is where that is per metric ton. Those are the things that we want per metric ton. So we can start way at the other end of the process, way at this end of the process, and we say now that we want 1,000 kilograms. So 1 metric ton. So 1,000 kilograms. 1,000 kilograms of pure ethylene glycol is how many kilomoles? What is the molecular weight? Somebody has a calculator, somebody is calculating, or they are not calculating. People are not calculating.
62.
Molecular weight is 62. So how many kilomoles are there? 1,000 kilograms. Are you with me or you are in some other world? Only
So
CR seems to, only CR seems to,
16.13.
only CR seems to be answering. Nobody else is doing any calculations. We should give all the marks to CR only. All others will get 0. Anybody is doing, not doing? Anybody is listening, not listening?
Yes, sir, we are there.
So calculate. Nishant, calculate. If I take basis as 1,000 kilograms of the product ethylene glycol, that's what we want. How many kilomoles is that?
16.13.
16.13. Now, if you take control volume like this, right, that 16.13 kilomoles are going out of this control volume. There is no ethylene glycol going out from this stream. So all the ethylene glycol must be coming, if we think in terms of kilomoles, all the ethylene glycol must be coming in from here, 16.13 kilomoles. Right? Now, if you take this as a control volume, our reaction is hydrolysis. Ethylene oxide gives you plus water, giving you ethylene glycol. And we are saying all the ethylene oxide gets hydrolyzed. So if I have to get 16.13 kilomoles of ethylene glycol, I should be starting with, in terms of kilomoles, I should be starting with 16.13 kilomoles of ethylene oxide. Right? If we think in terms of kgs, 16.13 kilomoles of ethylene oxide is how many kgs?
709.72.
709.72. Molecular weight. What is the molecular weight?
44.
44.
Right. Now 709 point. So I'm just going to go ahead with the solution. If anybody has a doubt at any point of time, please unmute yourself and ask. So now 709.72 kilograms corresponds to 10 weight percent. So the total, in terms of total kilograms, must be 7097.2 kilograms. And the water must be 90% of this total. So that is 6387.48. In terms of kilomoles, I will need to divide by 18. This will be 354.86 kilomoles. So now we know that 1 mole of ethylene oxide reacts with 1 mole of water. So out of this 354.86 kilomoles, 16.13 kilomoles will react with ethylene oxide, and we will be left with 338.73 kilomoles after the hydrolysis. And since no water is going in this stream, all the water must be going out of this fractional distillation column. So 338.73 kilomoles, that is 6097.14 kilograms. Okay. Now we can work backwards. We can go backwards. Now we can take control volume like this. We can take this control volume. Okay. Now 16.13 kilomoles of ethylene oxide are coming into this aqueous stream, right? If 16.13 kilomoles of ethylene oxide are coming into this aqueous stream, and we take this control volume, no ethylene oxide is going in this stream, in this gas stream, there is no ethylene oxide. So if we write in terms of kilomoles, this ethylene oxide must be 16.13 kilomoles. Okay. Or if you want, you can straight away take this whole thing as a control volume, either this as a control volume, or you take this whole thing as a control volume. We have 16.13 kilomoles of ethylene glycol, so straight away 16.13 kilomoles of ethylene oxide must be there, right? Now this 16.13 kilomoles of ethylene oxide that is produced in the reactor, 16.13 kilomoles of ethylene oxide that is produced in the reactor, how it is getting produced? 10% selectivity and 85% selectivity to ethylene oxide. Recall what we mean by conversion, what we mean by selectivity. So now if I take this reactor as a control volume, I can straight away calculate how many kilomoles of ethylene I should feed, right? So kilomoles of ethylene I should feed. Suppose I feed X kilomoles of ethylene oxide. Suppose we feed X kilomoles of ethylene oxide, sorry, X kilomoles of ethylene, not ethylene oxide, X kilomoles of ethylene to reactor. Ethylene oxide produced, conversion is 10%. So total amount of ethylene that reacts would be X multiplied by 0.1. Out of the total that react, 85% react to give us ethylene oxide. That is the selectivity. So ethylene oxide produced must be X multiplied by 0.1 multiplied by 0.85. This must be equal to 16.13. So now we can find out X. 16.13 divided by 0.85 divided by 0.1. This is straight away 189.76 kilomoles. Okay. So now,
Excuse me, sir. I'm sorry to interrupt, but I have a question. There's one of the streams which comes out of this entire system, which like contains still ethylene in it, like the entire control volume. There are some unreacted gases passing. It still contains ethylene in it, and at the end of the carbon dioxide removal process, we bring back the unreacted ethylene as recycled product. So that way, once we take the ethylene, unreacted ethylene, and put it back into the same reactor, it will reduce the amount of ethylene required to give the same ethylene oxide product, right?
correct, absolutely correct. But right now we are not doing this. Right now I have not shown. Right now I have not shown this arrow going back. I have not shown this arrow, right? Right now we are not doing that kind of problem. We will do this problem with this recycle once again after the mid-sem.
Okay, sir.
Okay, so you are right that this ethylene will go back. It will reduce the requirement of fresh ethylene. Absolutely, you are correct. But we will do it later, not just now. Just now I am saying that this goes somewhere.
Okay, sir. I understood, sir.
It just goes out somewhere. Right now, just worry about it. Let's not worry about it. Let's just say it just goes out somewhere. Okay, so
Okay,
this
sir.
X will be 189.76. Now, once I have this moles of ethylene, kilomoles of ethylene in the fresh gas, I know the volume percent, so I can calculate oxygen. I can calculate how many kilomoles of oxygen will there be. I can calculate how many kilomoles of methane will there be. Once I do this, then this is like your previous problem. Then this is like your previous problem. Where did that go? Ethylene oxide problem we had somewhere. We had this ethylene oxide problem, right? Isn't it? So then this becomes fairly straightforward to calculate this, calculate this, calculate this, calculate this, calculate this. Now we add water to take out ethylene oxide, and we know that this is to be 10%. So all the water that is here, the 709.72, right? So all the water that is here, right? Where is that water going to come from? There is no water going out here. There's no water going out here. So when we do control volume over this red control volume, all the water must be what is present here plus what I'm extra feeding. So then we can calculate this amount of water required. We can do all these calculations. That's also very straightforward, right? So this is how you would solve this problem. Can we go to the next problem?
Yes, sir.
Only CR is listening.
Yes, sir. Yes, sir.
Okay. Here is the next problem. How do you think sulfuric acid is made?
Contact process.
Contact process. So what does
SO2.
contact process start with?
Burning of sulfur or pyrites in presence of air.
Right. So let's say burning of sulfur. So you take sulfur, you burn sulfur. How do you burn? What do you supply for burning?
Oxygen.
Oxygen.
Air.
Right. So we don't supply oxygen, we supply air. And let's say we are supplying air 100% excess of what is required to make sulfur go to SO2. Okay. So what will come out of this burning process? What gases will come out?
SO2, N2, O2.
Right. So there will
SO2.
be SO2, there will be O2, there will be N2. We are saying 100% combustion of sulfur. No sulfur remains unreacted because we are supplying such a high amount of air and it is a nice combustion process. So we will have SO2, O2 and N2 coming out of this reactor, but of this combustion reactor or burning process, whatever you want to call. Now, what does that contact process involve? We have to convert this SO2 into SO3. So there is a catalytic reaction. Vanadium pentoxide is the catalyst. 450 degrees centigrade is the temperature. SO2 plus O2 will give us SO3. So what we are going to assume now is, actually this is not correct, okay, but we are going to assume for simplicity, just for us to solve the problem, we are going to assume 100% conversion of SO2. Okay, actually it is not in one step. You oxidize, you absorb, again you oxidize, again you absorb, again you oxidize, again you absorb, again you oxidize, again you absorb. So that is called as double contact, double absorption process. This SO3 that is formed, we absorb in water, DCDA, because this is an equilibrium reaction. So it doesn't go to completion. So SO3 forms, equilibrium is reached. You remove the SO3 by absorbing in water. So now more SO2 can go to SO3, and that's how you do reaction, absorption, reaction, absorption, reaction, absorption, right? So double contact.
So
Yes.
we are actually using Le Chatelier's principle of removing the products to shift the make the reactants into products, right?
Correct, correct, absolutely. That's how we are removing the SO3 by absorbing in water. But just for simplicity, we are saying right now that 100% conversion of SO2 to SO3 happens. Okay, it is not correct right now, but for simplicity, we are making that assumption. Okay, so we are saying now 100% conversion of SO2 happens. So what will come out of this catalytic reactor is SO3, oxygen, and N2. So now we have to absorb this gas. So this is a gas stream. This is a gas stream, high temperature. This is also a gas stream. This is molten sulfur. This is air, obviously gas, right? So far, so good. So we have to absorb in what?
Sulfuric acid.
Sulfuric acid.
Right. So we will absorb in sulfuric acid, but it is not just sulfuric acid. It is, let's say, we are absorbing in 93 weight percent H2SO4. Okay. Which means 93 weight percent is H2SO4, 7 weight percent is water, aqueous solution. Okay. So what will happen to the concentration? What will happen? SO3 will react with water and you will get H2SO4. So the amount of H2SO4 will increase. So after absorption, this becomes 98 weight percent H2SO4. Is that okay? Actually, it becomes oleum, but right now let's assume that it becomes like a 98% by weight H2SO4. And this remaining gas goes out. What is the remaining gas going to contain now? Oxygen and N2. We are going to assume that 100% absorption of SO3. We are going to assume that all the SO3 is absorbed. Is that okay? So no SO3 goes out. Only oxygen, unreacted, nitrogen anyway is inert. So it is going to go out. Oxygen and nitrogen will not get absorbed in this 98% by weight sulfuric acid. Is the process okay with everybody? Everybody comfortable?
Yes, sir.
Sir,
Yes.
why we are putting 98 weight percent H2SO4? We can
Why
only
we are?
put water. Why we are putting 98% H2SO4? We can only put water, no?
No, we are not putting 98%. We are putting 93 weight percent H2SO4.
Yes, 93%, sir. Why? We are
Why? Because we want to make 98% by weight H2SO4. 98% by weight H2SO4 is easy to transport. The amount of water is very small. Otherwise, if you have to sell your sulfuric acid, it will be so much amount of water will have to be transported from your plant to a plant where somebody is going to buy your sulfuric acid. So actually what is sold is oleum, which is SO3 plus pure H2SO4 mixture. But for simplicity, we are taking it as 98% by weight H2SO4. Is that okay?
Yes, sir.
So why we are taking 93% and why not pure water? If that is your question, just hold on for a minute. Okay. So if your question is why 93%, just wait for a couple of minutes. Okay.
Yes,
Om?
sir. Yes, sir.
Now, so far so good. Everybody comfortable with this?
Yes.
Now, where is this air going to come from? This air is going to come from atmosphere. Okay. So let's say it has oxygen and nitrogen only, mole percent or volume percent 21 and 79. Okay. But we will consider one more complication. Do you think atmospheric air has only nitrogen, oxygen? Forget other gases, okay? Forget carbon dioxide, forget argon and all that. There is one more component that is there along with this oxygen and nitrogen. What is that component?
Water.
Water.
Water. It is not water as liquid water.
Water
It is
vapor.
water vapor. So water vapor. How much water vapor do you think is there?
Depends from region to region.
Depends on
Region to region.
region to region. It not only region to region. It depends on
Humidity.
morning, day, night,
Humidity.
humidity, right? So let's assume right now that there is 20 grams of water vapor per kg of dry air. So when I say dry air, what I mean is oxygen and nitrogen mixture we call as dry air. So oxygen nitrogen mixture we are calling as dry air. And along with this dry air, there is water vapor. So we are going to say that this air contains 20 grams of water vapor per kg of dry air. Okay. Now, if this water vapor is there and I supply this air here, there will be water vapor in the stream coming to the burner. There will be water vapor going out of the burner into the catalytic reactor. Do you agree with that? Yes or no?
Yes, sir.
Yeah.
So this water now is a problem because the catalyst will get deactivated, will react with this water, vanadium pentoxide will react with water and all kinds of things will happen. Catalyst will get deactivated. You will have to replace the catalyst in no time. So this water vapor is not to be allowed in this stream. If water vapor is not to be allowed in this stream, I should not have water vapor in the air stream coming into the burner. That means I need to make this air bone dry. Right? It's called as bone dry. Means like a bone, it is so dry that there is no water vapor. So I need to dry this air. All right. Do you understand why drying of the air is required?
So it would even create side reactions also, right?
Okay, forget the side reaction just now. Anyway, catalyst activity is most important. You don't want to replace catalyst every now and then. Now, how do you think we will dry this air?
So by liquefaction, by cooling the air, which is
Do you
Or
see
by taking a
any
desiccating agent,
yeah, say that again.
Desiccating agent.
Desiccating agent. What is a good desiccating agent?
calcium
Silica
chloride,
balls.
Silica gel, okay, or calcium. You were saying we have
chloride, calcium chloride,
calcium chloride. On the TV screen or on your monitor, do you see any good desiccating agent?
sulfuric acid,
Sulfuric acid itself is a good desiccating agent. So what we will do is we will take a part of this stream, we will send it to this dryer. So the sulfuric acid will absorb the water and it will become dilute sulfuric acid. So this is product sold. So this is now our 98% by weight sulfuric acid. 98% by weight sulfuric acid will absorb water vapor from air. It will become diluted sulfuric acid. Do you see any use of the diluted sulfuric acid?
for absorption of SO3 intended lab.
Correct. So we will take this sulfuric acid which has picked up water vapor. It has become diluted sulfuric acid and we will send it to this. Om, does that answer your question?
Yes, sir.
Okay. Do you agree with all this? So we may need some extra water also here. We may need some extra water to be added. 93% by weight may not be enough to account for all the water vapor. Any problem so far? Everybody has understood this process block diagram? Yes, no?
Yes,
Any
sir.
doubt?
Yes, sir.
Anything you want me to repeat? Abhay,
Sir, can you repeat last part, sir? S2, SO4.
last part, which last part?
Means when we coming out, S2, SO4 coming out from dry air, so that.
So this is a block that is going to dry the air. So I send 98% by weight sulfuric acid to the stream. No water will go in the air stream to the burner. So it will become, let's say it becomes 93% by weight sulfuric acid, which we send back to the absorption tower.
Got it.
Okay. But the amount of 93% by weight and 98% by weight, amount of water that it needs to pick up may not absorb all the SO3 gas from here. So we may need extra water. May need.
Thank you, sir.
Okay, Atharva?
Yes, sir.
Shall we go forward?
Yes.
So calculate quantities and compositions of all streams per kg of sulfur fed to the burner. So if I have 1 kg of sulfur here, molten sulfur, that is fed to the burner, I would like you to calculate quantities and compositions of all the streams. So I have sulfur here in terms of kgs, 1 kg. So that's the basis that you can take. I wanted to calculate compositions and quantities of all streams. So again, for the last time in our lives, if it's a solid or a liquid stream, how will we express the composition? In what way?
Weight percent.
Weight percent.
If it is a gas stream, how do we express composition?
Volume percent.
Volume percent.
Volume percent. Okay, so do this problem. I'm here only. If you have any doubts, you can always unmute yourself and ask. Any answers?
So for the SO2, O2, N2, percentage volume would be 10.5.
Let's just do one thing. Tell me just one answer. How much water do we need to add, if at all?
Okay, sir.
If at all.
Sir,
Yes.
sir,
Oh, just speak loudly. Your voice is very faint.
sir, 100% excess of air means 100% excess of oxygen, no? Uh,
I don't know.
Sir, means if I calculated the 100% excess means air with respect to sulfur, then will I have to take 21% of that for oxygen moles?
This air is 21% oxygen, 79% nitrogen by moles. I don't know about this air.
So, sir, means after removing the total moles of air, so we have to means do 21% of that to get the oxygen mole.
You do whatever you want.
Sir, if I do that, then means it is not working. Sulfur is not getting completely reacted.
I don't
So,
know. Something calculation mistake you are doing.
okay, sir.
Go back to our previous problems. Look at this problem. Look at this problem where we talked about air, excess air. Somebody asked whether excess air should be excess oxygen or excess air. Look at what we were doing here. Om, are you able to see?
Yes, sir.
Look at what happened here. How we calculated excess air. Whether I calculated based on oxygen or whether I calculate based on air. Finally, we are getting the same thing. Isn't
Yes,
it?
yes, sir.
Do you recall?
Yes, sir.
Do you have a notebook in which you are writing all these things or you are doing on some scraps of paper?
A notebook.
Excellent. So go back to your notebook, go back here. Go back to the second problem we did on combustion, how we calculated excess air. Okay.
Yes, sir.
It is 21% oxygen, 79% nitrogen on dry basis. This air that is coming in has some amount of water vapor. It has 20 grams of water vapor per kg of dry air. On dry basis, it is 2179. Amrapali, any questions?
So I'm solving.
Akash? Ansh? Any questions?
Sir, in the absorption of SO3, is there a reaction happening or it is just like absorption?
It is like reaction. Na? SO3 is getting reacted with water to give you H2SO4. Whether you call it absorption, whether you call it reaction, finally SO3 is coming in and H2SO4 is being produced.
So, what is
So
the
whether
role
it
of
remains
the
as SO3 water mixture or whether you call it as H2SO4, choice is yours.
Yeah, so the 93% is going as it is, but extra H2SO4 is added due to a reaction between SO3 and water.
Correct. No, otherwise how it will become 98% by weight?
Yes, yes.
Dharmik, any question?
Sir, the 93 weight percent H2SO4 which we have supplied, sir, that is the recycled one, right? That is the coming from the drying part.
Correct.
Yes, sir. So, sir, there is no external source of 93%, right?
Extra source of 93%. Which is the extra source of 93%?
No, sir. That is what I was asking for.
Keshav, answer.
So for the first cycle, do we consider that the water that is being dried, that is being used in the H2SO4?
Good point. Good point. So what we are going to say that this process is a continuous process and it has reached steady state. That means we are not bothering about the first cycle, second cycle, third cycle. It has reached steady state, meaning this air is coming in all the time. This 98% sulfuric acid is coming in all the time. This 93% by weight sulfuric acid is going out all the time. Bone dry air is going all the time. Sulfur is coming in all the time. Steady state means quantities and compositions are not changing with respect to time. This gas goes out at all times. This gas goes out at all times. This gas goes out at all times. This water is added at all times. This is added at all times. This is produced at all times. This is recycled partly at all times. Partly it is sold as product all times. Steady state. Quantities and compositions do not change with time. And quantities we will have to write in terms of kgs per hour. How many kgs per hour it is coming in, how many kgs, so many kgs per hour it comes in, because it is a continuous process. Continuously it is happening. Is that okay?
Yes, sir.
So we are not worried about first cycle, third cycle. First cycle happened at when there was Big Bang. So now 13.5 billion years have passed in the first cycle, and so steady state has reached. For the first cycle, we will buy 98% by weight sulfuric acid from outside, start the process, and then we will sell all that 98% by weight sulfuric acid. Nakshatra, answer?
Yes, sir, solving.
Okay.
So then we are using 93 weight percent H2SO4 and plus H2SO4 that is diluted, right?
Is there any other extra arrow that I am showing? Is there any other extra arrow that is shown for 93 weight percent? All the arrows are indicating all the streams that are coming in. This stream is going straight away here. Is there any extra fresh 93% we are adding? Is there any other arrow that you are seeing?
So no, as in my doubt is that we are diluting the H2SO4 to 93%, right?
Right.
Okay, sir.
It is the same stream. This arrow is going to continuing here, no? Is there a discontinuity in the arrow?
No.
It is the same arrow. That same arrow means what? The same stream.
Okay, sir.
All right.
Sir, H2 added is 625 gram.
Thicker arrow. What are you saying?
625 gram H2O added, water added.
625 grams. All right. Answer. Kgs of water added. 0.625. Who was answering that? Atharva, you were answering. Who was answering? Who was answering? Atharva, it was your answer?
Yes, sir.
Okay.
Sir, O2 and N2 volume percent.
Darshan, what are you saying?
O2 and N2 volume percent. I getting.
Where? Which stream?
Last stream.
No, I don't want that. I just want this water.
Okay, okay, sir.
This water.
Sir, can you explain once again the process after 98% of H2SO4 is emitted?
After this, after this 98% by weight H2SO4, this stream is partly sent back to the dryer and partly sold as product. Whole stream is not going back, otherwise we will have nothing to be sold. So we are selling this product, part of the stream, and part of the stream is sent back so that it becomes 93% by weight sulfuric acid. Okay or not okay?
Yes, sir. Okay.
Sir, I want to change my answer. I do not calculate one factor, sir. So it is 390.84, sir. 391, sir.
160?
0.391. So one no, sir. 0.391, sir.
And that's what I've written, remember. That's what I had written.
Yes.
391. Who cares about that point one? Check your answer. I don't think it is correct. Atharva, check your answer. Check your calculations.
Yes, sir.
You are close, but not. It is not correct. Something is missing.
Okay, sir.
So 0.453 kgs of water should be added.
Okay. 0.45. That's the second answer.
So I am also getting 0.453 kg of water to be added.
Okay, Sarthak. Karthik, any answer?
Yes, sir, at the last step.
Last answer or last step you are doing?
Sir, the last process.
Okay.
Sir, I'm getting 1.14 kg of water.
Say that again. Let me just write 1 second. Huh? How much you are saying, Ria?
1.14.
1.14 kgs. Okay.
Yes.
1.14.
Point 0.41, sir. 0.41 kg.
0.41.
So 0.45.
Yes, sir.
Yeah.
Sir, I'm getting is 0.215.
0.215. Looks like we need more space.
Sir, I'm also getting 0.45.
Okay. 0.45 seems to be a popular answer. Who was getting 1.14? Ria, you are getting 1.14? Who was telling me?
Yes, sir.
Just check your calculations. Something is wrong.
Yes, sir.
Praveen, any answer?
Not yet, sir. I'm trying.
Nishant, any answer?
Yes, sir. 2 minutes.
Okay. Dhruti, any answer?
Sir, I'm getting 0.55.
0.55. Okay. Bhakti, any answer? Aniruddha, any answer?
Solving, sir.
Sir, I'm doing so.
Okay. Ah, there are two Aniruddhs. I forgot. Yeah. Karthik, just go ahead, unmute yourself and ask.
No, sir. By mistake, I clicked the button.
Ah, okay, okay. Aryan Mehta, any answer?
Yes, I gave 0.45.
Ah, okay. Sorry, there's no way I can remember who gave what answer, especially in this virtual mode. At least in a class, I would recall who gave what answer. So if you have finished, if you think you've got an answer, just solve some problems from Himal Blaw's book. Don't spend time waiting for others. You just go ahead, solve any other problem from Himal Blaw's book.
So even I got 0.55.
0.55. Okay.
Sir, I'm getting 0.39.
0.39.
Hello, sir. Sir, are we adding water to make the solution 93 weight percent, or we are adding for the absorption process?
Where is the arrow going? Is the arrow going to the block, or is the arrow going to this 98%, 93%? Is the arrow like this, or is the arrow like this? Where is the arrow?
Yes, sir, it's towards the block. I got it, sir.
In any case, how does it matter if the arrow is joining here? How does it matter if the arrow is joining here? This is 93% by weight. This is 93% by weight. This, what goes to the absorption tower, will be slightly smaller. Maybe 91, 92, whatever it is, based on how much water is added. How does it matter?
Yes, sir, actually, I was thinking that after.
Whatever comes out of the air dryer is 93 weight percent.
Okay, sir.
How does that change your answer? Should we solve, or do you need more time?
Sir, more time.
How much more time?
Sir, 2 minutes.
Sir, I am also getting 0.39.
Point 0.39 and 0.454 seem to be two popular answers. Anybody wants hints?
So even I've got 0.55.
No, 0.55. Okay. So 0.55, 0.39, 0.45 seem to be popular answers. Priya, did you check your answer? Somewhere you had gone wrong.
Sir, I did, but I couldn't understand that.
Okay.
Sir, what process happens in the air dryer when the 98% H2SO4 is passed through it? I mean,
Water gets absorbed from the air becomes dry, and my water goes in 98% by weight sulfuric acid, and it becomes more dilute sulfuric acid. It becomes 93% by weight sulfuric acid. Sulfuric acid is a good dehydrating agent, isn't it? It has very good affinity for water. It loves water.
So,
Yeah.
Sarthak here, sir. So initially I got 0.45, but I want to change it to 0.39.
All right. So 0.39 seems to be popular answer. Somebody who had got this 0.41, maybe it is just some round of error you are doing somewhere.
So 0.408 is my answer. To round of 0.41.
Just check somewhere else. Have you made some mistake?
Okay, sir.
Slight mistake. It may not be something major. Who had got this 0.215? Anybody got this 0.215?
Yes, sir, me.
Sir, I've got the answer as 0.22.
Sir, I am getting 0.09.
So 0.39. I'm getting 0.45.
Okay, shall we solve the problem?
Yes, sir.
Okay, so let's look at the solution. Maybe you have the answer, you don't have the answer, it doesn't matter, but let's try to solve. So we are told that basis, or we want to calculate everything per kg of sulfur. So if I take 1 kilogram of sulfur, that is 1000 grams of sulfur. If I divide by atomic weight, I could write in terms of gram moles. Gram moles would be 31.25 divided by 32, right? Sulfur atomic weight is 32. Okay, so 31.25 gram moles of sulfur come in. As per stoichiometry, I will require 31.25 gram moles as per stoichiometry. But we are not providing as per stoichiometry, we are providing 100% excess, which means we are providing another 31.25 as extra. So the total amount of oxygen that will come in would be 62.5, 31.25 multiplied by 2, 62.5 kilomoles. Now, sorry, not kilomoles, this is gram moles, because we are talking sulfur also we have taken as in terms of gram moles. Okay, now 62.5 corresponds to 21 mole percent. So nitrogen would be 79 by 21 multiplied by 62.5. So 79 divided by 21 multiplied by 62.5. This number, this number would be 235.12. Now, if you do control, if you take this air dryer as a control volume, all the oxygen and nitrogen that we are supplying must be coming from this fresh air. On dry basis, it is 2179. So this oxygen must be 62.5. This nitrogen must be 235.12. Okay. So now, if we say 62.5 gram moles, we can convert this into kgs as well. Right? 62.5 gram moles would be 62.5 multiplied by 32 gram, that is the molecular weight of oxygen. This will become 2000 grams. So this becomes 2 kgs. 235.12 is the gram moles of nitrogen multiplied by 28, that is the molecular weight of oxygen. This becomes 6583.36 grams. So I'm just going to write it as 6.583 kilograms. So the total amount of dry air on dry basis that is supplied is 8.583 kgs. So the total water coming in from the air contains 20 grams of water vapor per kg of dry air. Dry air is 6.583 plus 2, that is 8.583. So this would be, I should say total, not water, I should say water vapor. Okay, because water, I mean it is liquid. So 8.583 is the total kgs. Every kg is going to contain 20 grams, right? So this would be 8.583 kgs multiplied by 20 grams per kg. This would be 8.583 multiplied by 20. This would be 170 1.66 grams of water. Grams, be careful about grams, kilograms. Right? Now we take this red thing as a control volume, air dryer as a control volume, nitrogen we have taken care of, oxygen we have taken care of, that is anyway remaining unreacted. So all we have to do is water balance we have to do across this sulfuric acid coming in and going out. So if you think about this air dryer, right, 171.66 grams of water come in as water vapor, 98% by weight H2SO4 comes in, 93% by weight H2SO4 goes out. So if I draw the table, what comes in, what goes out, H2SO4 weight percent, if I write 98 and 2 grams, I can write here also H2SO4 and water I can write weight percent. Oops. H2SO4 and water weight percent, it is 93 and 7. I want to find out how many kgs of this 98% by weight comes in. So if I say x grams come in, this would become 0.98 x grams. This would become 0.02 x grams. H2SO4 is remaining unchanged. Water is only getting added. This is like the problem that we did long time ago. This is 0.98x. This would be 0.02x plus 171.66 grams. Right? So now we know that this corresponds to 7 weight percent. That means 0.02x plus 171.66, or if you like, this total would be x plus 171.66. So 0.02x plus 171.66 divided by x plus 171.66. This must be 7%. So that is 0.07. So somebody calculate x from here. Somebody calculate. Somebody calculate. Anybody around?
Yes, so 1 minute.
Takes so long.
Sir, 3192.8. 0.9.
Oh.
Yes, sir. It's fine.
3192.9 grams. So this is 3192.9. This is 3192.9 plus 171.66. This will become 3364.5 grams. 3364.5 grams. So now we can go forward. We have got this stream. 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 Okay, now we can go forward. SO2, 1 mole of sulfur burns, 1 mole of SO2 will be formed. So this will be 31.25 not kilomoles. Now We are talking about gram moles. Okay. Oxygen, out of the 62.5, 31.25 are going to react. 31.25 will remain unreacted. Nitrogen, everything will remain unreacted to 35.12. So we've got everything up to this stream. Now let's go forward. 1 mole of SO2 reacts, I will get 1 mole of SO3. So this will be 31.25, again not kilomoles, we are talking about gram moles. Okay. Oxygen, every mole of SO2 reacts, half a mole of oxygen is going to react. So 31.25 reacts, 31.25 into 0.5, those many moles of oxygen will react. Correspondingly, 31.25 minus 50% will remain 15.625 gram moles, and nitrogen also will be now same to 35.12 gram moles. Correct? Now we have got everything up to here. So far so good. Anybody has any doubts so far? Any difficulties so far?
No, sir.
Okay.
No, sir.
So now we have got this stream, right? Which is the same that this stream. Okay. Oxygen, nitrogen, same gram moles. Nothing is going to happen to them. So this is 15.625. This is 235.12. Now all I have to do is take this as a control volume. Okay, let me do that. Let me take this as a control volume. SO3 in terms of gram moles. O2, N2 I am not writing because anyway they are there, but I don't have to worry about that. SO2, SO3 is 31.25. H2SO4 is there. Water stream is there. This is weight percent. It is 93. It is 7. Total is, how much is total? 3364.5 grams. 3364.5 grams. All right. Fresh water I might have to add. Whatever nitrogen and oxygen is here, same amount of nitrogen and oxygen is going out. So I don't have to bother about it. This, whatever goes out, is H2SO4 and water. This is 98, sorry. If we write in terms of weight percent, it is 98 and 2. Right? Grams, we can write grams and we can write gram moles as well. Okay. So this is 3364.5 grams, 3364.5 grams, out of which 98% is H2, sorry, 93% is sulfuric acid. So 3364.5 multiplied by 0.93, that is 3129 grams is H2SO4. 3364.5 minus 3129, 235.5 gram moles, grams of water there will be. So 3129, we can convert into moles. This will correspond to 31.93 gram moles, and 235.5 divided by 18, it will correspond to 13.08 gram moles. Do you agree with this? Everybody okay so far? Everybody okay with this stream? Everybody okay with this stream? Yes, no?
Yes, sir.
No, sir.
Okay.
Yes.
Now what is happening in this absorption process? What is happening? SO3 is getting absorbed in water and giving us H2SO4. So every 1 gram mole SO3 that reacts, 1 more gram mole of H2SO4 is going to form. So I have 31.93 that is added from this stream, plus 31.25 gram moles are going to react with water. So 31.93 plus 31.25, this would become, in terms of gram moles, if I write, this would become 63.18 gram moles. Okay. Grams, if I write 63.18 into 98, this will become 6191.64. Now that corresponds to 98%. So total, if I write divided by 0.98, this will be 6318 grams of total. 2% is water, so multiplied by 0.02, that is 126.36 grams is water. Okay, now water balance, 13.08 gram moles of water are coming in, plus I require 1 gram mole of water per gram mole of SO3, right? So I want 31.25 gram moles of water to react. What comes in is 13.08. What goes out, gram moles. What goes out, I want in terms of gram moles. Now it will be 126.36 divided by 18. I want 7.02 gram moles to go out. What goes out is 7.02 gram moles. So now if I am doing water balance on this control volume, what water balance can I write? Water coming in from, let's call this as stream number 1, let's call this as stream number 2, let's call this as stream number 3, let's call this as stream number 4, let's call this as stream number 5. Water coming in from stream 1 plus water coming in from stream 2 plus water that has reacted in the absorption process must be equal to water going out in stream number 4. Do you agree with this? Do you people agree with this? Yes, no?
Yes, sir.
Right. So water coming in from stream 1, that is 13.08 gram moles. Water coming in from stream 2, I don't know that, let's put that as X. Water reacted, 31.25 gram moles of water I want to react. Water goes out, how much water goes out?
It should be minus
7.02. Say that again. Oh, sorry. Right. Right. Water reacted. Okay. What comes in minus what reacts must be equal to what goes out. Thank you. Whoever it was. Who was it?
Sir, Arya.
Arya. Yeah. Thank you. Thank you. Thank you. Water comes in minus what reacts must be equal to what goes out. Sorry. Thank you about that. So this X would be 7.02 plus 31.25 minus 13.08. So this would become 25.19 gram moles. In terms of grams, this would become 25.19 into 18. This would be 453.4 grams, right? Or 0.453 kgs. Do you agree with this? Everybody comfortable? Everybody okay?
Yes, sir.
Can we go to the next problem?
Yes, sir.
Yes, sir.
Okay, let's go to the next problem. Right, next problem also is a little long, so I will give you the problem and then we will solve the problem and we will see the solution later. Okay. We will have plenty of time to do this problem.
Sir, could you please show the previous slide for a second?
Somebody is asking something. Please go ahead. Speak loudly.
Please show the previous slide. Just once.
I'm unable to hear you.
Please show the previous slide.
Previous slide. This.
Thank you, sir.
Anything? Any problem? Any question?
No. No, sir.
Edith, you were asking. Who was asking?
I've confirmed what I wanted to check. Thank you.
Okay. Got it? Can we go forward?
Yes, sir.
Okay. All right. Can we go forward? Can we go to the next problem? Any other question? Shall we go to the next problem?
Yes, sir.
Yes, sir.
Okay. So next problem is about ammonia manufacturing. So ammonia reactor. How is ammonia made? In Haber process. What do you supply to the reactor?
Nitrogen and hydrogen.
Nitrogen and hydrogen.
Nitrogen and hydrogen.
Right, nitrogen and hydrogen. In what ratio we want?
1:3.
1:2.
All right. So 1:3. So reaction is nitrogen. Oops. Nitrogen plus hydrogen giving us NH3. So if you balance this reaction, you require nitrogen and hydrogen in the ratio 1:3. That means I want nitrogen to be supplied to the reactor. I want hydrogen to be supplied to the reactor in the mole ratio 1:3. Isn't it? Do you agree with this?
Yes, sir.
Yes, sir.
Now, what is a good source of nitrogen?
Heating azides.
Air.
Heating azide. Who was saying that?
Sir, me, Arya.
Arya. Heating azide. What azide? Which azide you want to take?
Sodium azide.
Sodium azide. All right, we will take sodium azide. Why do you want sodium azide? Why not cesium azide?
Sir, because cesium would be more expensive than sodium.
So sodium azide is NaN what? NaN3 or what?
NaN3.
NaN3. So you will heat NaN3 and do what?
I'll get sodium plus nitrogen gas.
Okay. What will you do with this sodium?
So it will would not be able to use it. It would instantaneously convert into sodium hydroxide or sodium carbonate after reacting in the air.
So it will react with air, right? So you will get sodium oxide. It will react with water in the air. It will give you sodium hydroxide. So these are nice safe processes, or these are very hazardous processes? Have you ever handled sodium in your 12th standard lab?
No.
No. Well, unfortunately,
Yes.
you didn't have your first year chemistry lab also, or first year lab also. Otherwise, sodium is very, very dangerous. We don't want to handle sodium. Further, we have nothing to do with the sodium. What we want to do is make ammonia. Why should we involve sodium in the process? So azide, all the chemical reactions that you have seen in 12 standard textbooks, 11 standard textbooks, they are good for that only textbooks. They are good for nothing else, because you are not worried about stoichiometry, you are not worried about cost, you are not worried about environmental impact when you are in 11th and 12th standard. Safety you are not worried about when you are in 11th and 12th standard. So practically all the reactions that you have studied in your 11th and 12th standard are good for 11th and 12th standard only. Okay, any other safer, easier, cheaper source of nitrogen that you can think of?
Air, sir.
Air.
Air. Ah, very nice. So air is a good cheap source of nitrogen. Nitrogen, oxygen, dry basis. Let's assume this air is dry. Mole percent 79.21. Unfortunately, when I take nitrogen from the air, oxygen comes free with that nitrogen. I don't require nitrogen in the process. I require nitrogen in the process. I don't require oxygen in the process. Is there any way, do you think, I can get rid of oxygen?
Distillation, dry distillation.
Distillation. Okay. Oh, distillation. Any other easier way of getting rid of oxygen? Pardon? Any other good way to get rid of oxygen? Somebody must be thinking pyrogalol, absorption in pyrogalol or something like that.
Diffusion.
Diffusion. Diffusion of what?
So we can, at a particular temperature, both of them would have different rates of diffusion.
All right. Is there any easier way of getting rid of oxygen without affecting nitrogen? Do you see any good way here on the screen? Where we get rid of oxygen, keep nitrogen.
Combustion.
Combustion, right? So if I have methane, I can do oxidation. Let's assume that we will have stoichiometric amount of methane and stoichiometric amount of oxygen, so that our reaction methane plus oxygen giving us carbon dioxide and water will happen. So what will come in this gas stream? Methane, let's assume all reacts. Oxygen, let's assume all reacts. Stoichiometric proportion. So nitrogen will remain unreacted. Oxygen will go away, methane will go away, carbon dioxide will be generated, and water will be generated. All right. Now I have got rid of oxygen, but I have got carbon dioxide in the process, I have got water in the process. I don't want carbon dioxide also and water in the process also. Any other way you can think of getting rid of water?
Desiccating agent.
Desiccating agent. There is yet another way.
So, sir, we can add K2CO3. Water and CO2 both will react.
Water and CO2 both will react. Okay, we don't do that. There is a reason why. There is a reason why we don't do that. In this stream, along with methane, we also want, let's say, carbon monoxide. So we will have carbon monoxide in this stream as well. So we do something called as shift reaction, water gas shift reaction. So carbon monoxide plus water, they will react to give us hydrogen and carbon dioxide. So now we will have nitrogen, we will have carbon dioxide, we will have hydrogen. Okay. The water and carbon monoxide both will go away. It will react with each other to give you carbon dioxide and hydrogen. See, we want that hydrogen, right? So that hydrogen is required here. 1 second, let me complete. Now, this carbon dioxide we need to get rid of. So then we can have this K2CO3 and KHCO3, all the things that we saw for our previous question, CO2 removal system. Now CO2 will go away. Now we will have only nitrogen and hydrogen. Now, question is, how do I get this carbon monoxide in the first place? So that carbon monoxide we generate by a process called as reforming. So what we do is we supply methane, steam reforming, high temperature. We have water, means steam, water vapor. So CH4 plus H2O giving you CO and hydrogen. Okay. But we don't use up all the water because we want water to be present here as well. We want water to be present after the oxidation reaction. So the stream coming out of the reforming, we will not allow all the methane to react. Anyway, it's an equilibrium reaction. We will have methane, we will have water, we will have carbon monoxide, we will have hydrogen. Okay. That stream goes to that partial oxidation where methane reacts with oxygen to give us carbon dioxide. Water is generated plus some water is coming in, and then this hydrogen in this partial oxidation, let's assume that hydrogen does not react, let's assume that carbon monoxide does not react, so we will have hydrogen here as well. And if there is hydrogen here as well, it does not react in the water gas shift reaction, in fact it is produced in the water gas shift reaction. I will have hydrogen going out here as well. Right. So effectively, the steam reforming of methane, this provides the hydrogen that is required here for the reaction. All right. Arya, you were asking something?
So can we like, why are we supplying carbon monoxide in the oxidation stage also? We can just add it in the shift reactor.
Yeah, we can add it in the shift reactor, but where are we going to get carbon monoxide from? Carbon monoxide is going to come from steam reforming. So if I divert this stream not to oxidation but to here directly, methane will also come here. Isn't it?
Yeah.
I don't want that methane because I don't want methane remaining here. If I don't want methane remaining here, I don't want methane here. If I don't want methane here, I don't want methane here. Material balance. Do you agree?
Yes, sir.
So this is how ammonia is manufactured. In a plant. Is everybody okay with the process?
Sir, what is the conversion rate in the reforming process?
I don't know.
Okay, sir.
There's no conversion rate. It is called as percent conversion.
Yes, sir.
I have no idea. So I would like you to calculate all quantities and compositions per metric ton of ammonia produced from the reactor. Okay. It's a continuous process operating at steady state. All right. Will you be able to try? Yeah.
In the oxidation, there would be a side reaction of hydrogen also being oxidized and carbon monoxide also
Yeah,
being
that's what I was telling you. In the oxidation, let us assume for simplicity, just because we are in the first year, we will make an assumption that carbon monoxide does not react with oxygen, H2 does not react with oxygen. Actually, if you look at the plant, if you think about it, the oxidation and reforming, you can reverse also. You can do oxidation first and then you can do reforming, or you can do reforming first and oxidation later. It does not matter. Both kinds of plants operate in the world, but for the purpose of this problem, because we are in first year, we are going to make an assumption that carbon monoxide and water and hydrogen does not react in this oxidation process. Only methane reacts, and methane and oxygen are in stoichiometric proportions. I have 100% conversion of methane and therefore no methane remains, no oxygen remains in the gas coming out of the partial oxidation process. That's why it is called as partial oxidation. Is that okay? This is a simplistic picture because we are in the first year. Is that okay?
Yes, sir.
All right. So will you be able to solve? You have 2 days to solve. Shall we stop here for the day?
Yes, sir.
Any other quick question? I'll stop.